Let me give you a real-world example to illustrate not only identifying the critical assumption, but also doing low-cost experiment to resolve that assumption. The company is IBM. IBM, as you know, in the early 90s, went through a very punishing period where the company was starting to lose tremendous amounts of money. Then Lou Gerstner became the CEO. And Lou Gerstner very quickly got the house in order. He did a lot of good work in Box One for the first 5 years of his tenure. But then he knew if IBM had to really become a leader in the future, he has to start Box 3 experiments. And you will particularly remember those days, not only IBM was in trouble in the early 90s, the good employees didn't want to work for large companies like IBM. Silicon Valley was the cool thing to be. So he was fighting a lot of perception about big companies and in particular about IBM. If you remember, in the late 90s, one of the things they did to make it appear IBM is cool is Deep Blue. And Deep Blue went on a chess match with Garry Kasparov, the world chess champion, and beat Garry. That indicated to the world IBM can do cool things. But he wanted to continue that in building Box 3 innovation. One of the Box 3 innovations IBM started was in 2002. IBM in 2002 had the fastest supercomputer in the world. Unfortunately, in the year 2002, NEC, the Japanese computer company, built a supercomputer faster than IBM's. So IBM lost its edge in the supercomputer segment. So one of the things the CEO of IBM decided to do at that time was to really create a Box 3 move by creating a computer which is 500 times faster than the supercomputer that was available at that time. Now, you wonder, where do you need a supercomputer which is 500 times faster than what was available in 2002? You see, take a topic like global warming. Global warming researchers were doing so many simulations. They were analyzing so much data. The capacity of current supercomputers were inadequate. At the same time, there was another explosion in research in biotechnology. Really, the genetic code of human beings, people were wanting to define the human gene. And the human genomics required many thousands of simulations. And the current capacity of supercomputers were not adequate. So IBM decided they will actually come up with a supercomputer which is 500 times faster than what was available at that time. That is clearly a Box 3 move. In fact, they even named that supercomputer as Blue Gene. And gene is to appeal to the genetic engineers. Now, here was the real critical unknown in this. You see, the way you speed up a computer typically is to increase the power of the microprocessor. When you increase the power of the microprocessor, the computer is able to handle more data. But everybody agreed the current trajectory by which you create supercomputing has reached practical limits. That means the size, the speed of the microprocessor cannot be increased further. The reason being, for instance, if you wanted to create a supercomputer 500 times faster than what was available, you have to create a microprocessor whose size would be the size of a football field. And that microprocessor, as you know, is a copious consumer of electricity. You have to put a dedicated power plant just to power one such computer. In fact, the cost of electricity will far exceed the cost of computer. Therefore, people kind of gave up that it is not possible to increase the speed of supercomputing using the box one approach, which is to build more and more powerful microprocessors. So what IBM decided to do was to come up with the box 3 move. And the box 3 move is, instead of using sophisticated and fast microprocessors, they decided to use mundane basic chips. These are commodity chips. Individually, they could not power and analyze a lot of data. And individually, these commodity chips actually consumed very little electricity. They were tiny chips, but they didn't have much computing power. But IBM's breakthrough was, if I can use thousands and thousands of these commodity chips, and if I can network them, I can increase the speed of the computer. This particular box 3 move is called massively parallel computing. Instead of using one very, very superior microprocessor, you use many, many small mundane chips. But by networking them, you increase the speed of the computer. This is the box 3 concept IBM came up with, massively parallel computing. But the critical unknown in this project is what is known as network congestion. Now, let me give you a metaphor so that you can understand what I mean by network congestion. Imagine Los Angeles highway. Suppose there is one automobile going on that highway. That is like one commodity chip that is powering the computer. Now, let's say 5 people can sit in that automobile. That means on that highway, 5 people are transported. Suppose you put 2 automobiles on Los Angeles highway. Then 10 people are merrily traveling on that highway. Therefore, when you add another commodity chip, obviously the computing power goes up. Suppose you add a 3rd automobile, now 15 people are traveling beautifully on Los Angeles highway. Imagine, suppose you dropped 100,000 automobiles on the highway. Suddenly, there is a traffic congestion. Because of traffic congestion, actually, the traffic comes to a dead stop. Therefore, nobody goes. This is the main problem. This is the main unknown in massively parallel computing. Because there is no linear relationship between the number of commodity chips and the speed of the computer. At some point, when you add more chips, actually the speed comes down. So you need to find that optimal point where you can build a computer which will give you maximum speed with absolutely the minimum use of commodity chips. But you can't analyze this theoretically. This is the main problem. This is a weak signal. You know, when you add more commodity chips, the speed goes up. What you don't know is, where is the optimal point? You can't build a large computer to find this out. That will be too expensive an experiment. So in order to resolve this critical unknown, what IBM researchers did, IBM dedicated team did, was first they combined 2 commodity chips. The speed was going. This is what is called rapid prototyping. Then they did another experiment where they doubled the size of chips. Now it is 4. Still the computing is fast. Then they doubled it again, make it 8. Still it is going fast. Then they added another 100% more chips. It's now 16 chips. Now it's again going fast. In fact, one of the theoretical papers that was published by an MIT researcher said 512 is the optimal size of the chips. Beyond 512 chips, the speed of the computer will come down. But that was just a theoretical analysis. So when they started doing experiments in a systematic, low-cost way and accelerating the prototype, finally, Blue Gene was constructed with 600,000 chips. Something they would have never known up front. 600,000 chips is where, until that point, the speed of the computer was going up. By the way, the Blue Gene beats NEC's supercomputer by a mile. And that was one of the major success stories for IBM's box 3 move. And that illustrates why it is so important for you to identify the critical assumption. If that assumption proved to be wrong, there is no reason for them to be working on that supercomputing trajectory. And once you identify the critical assumption, then the next job is to find inexpensive ways to resolve that assumption.